Okay, this is the lecture video for MAC1140 pre-calculus. We're in section 11.5 where we're going to be taking a look at partial fraction decomposition. Now, the procedures that we're going to be talking about have to do with rational expressions, and if you recall, rational just means a fractional expression where either the denominator is a polynomial or the numerator or both. So here you see two rational expressions, and the experience that you have had is in the previous two classes, MAC 1105 and MAC 1033, you might have been asked to either add these rational expressions or subtract them, needing a common denominator to do so. So what you're seeing here is that they've already found the common denominator, which would be this denominator would have to go into the common denominator, which we call the LCD, least common denominator, as well as the x minus 3. So that's what the denominators of both of them would have to be. And if you remember when you were working with these in the previous two classes, if you wanted these denominators to match, you would just look at what is presently in the denominator, and therefore you would compare it to the LCD to see what do I need to multiply to make this denominator look like the LCD, which in this case would require the x minus 3, that's the piece that it needs in order to make it look exactly like the LCD. And you learned that whatever you multiply the bottom by, you have to multiply the top by. So just so you can follow this example, I'm going back to things that you learned in the previous course before we go on to what we're going to actually talk about here. So that would make this denominator the way you want it to be. And then this denominator, in order to make it look like the LCD, you'd have to multiply by the x plus 4, always multiplying by the same thing on the top and the bottom. Okay, so maybe now you can follow what's going on over here. So if you were to multiply the bottom by x minus 3 and then also do it to the top, that's where they got the 3 times x minus 3, which you're seeing right here. And then to make this denominator look like the LCD, they multiplied by x plus 4, thereby having to use the same thing at the top, and that's where they get the 2 times x plus 4 that you see right here. So that explains these two brand new numerators in an attempt to get a common denominator for both of these fractions so that you could actually carry out the addition. And what you end up with is after you've actually carried this 3, distributed it through the parentheses, giving you 3x. Here, if you carried the 2, 3, you'd have 2x. So 3x and 2x is where they got the 5x. If you carried the 3 completely through to the constant, it would be negative 9. And here you'd get an 8. Those combined is where they got the negative 1. What you're actually going to be doing in this section is you're going to be starting with this this answer that you're seeing here and taking it in the reverse direction all the way back to what's called the partial fractions. These two partial fractions come from this actual singular fraction. And the process that as we go from this answer back to the partial fractions is called partial fraction decomposition, where you go from the fraction where you've gotten the common denominator, and what you're seeing here is just those multiplied out, and here they've distributed and collected like terms, which I already went through. So that's just a little background on what you're actually doing. It's the reverse procedure that you have gone through in your previous courses. A little bit of terminology that I'm going to throw at you, because typically the first 2 or 3 questions in MyLab Math, they're just basically asking terminology definition, seeing if you've read the theorems. So just remember that these are called rational expressions, and a rational expression can either be proper or improper. And so there is a definition of what proper means right here. A proper rational expression just means the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator. So, I mean, you could write that in a little bit shorter way just to help you remember it. When the degree of the numerator, I'm going to put NUM for numerator, kind of like a little subscript, when the degree of the top is less than the degree of the bottom, which is called the denominator, then we call that an improper rational expression. Okay, so that's one of the terms. They'll also probably ask you about the term irreducible. I'll bring that up later in this section. So if the degree of the numerator, what's in the top, whatever polynomial is up here, and remember the degree goes by whatever is the term with the highest degree. That dictates what we call the degree of the entire polynomial. So if the degree of the top is less than the degree of the bottom, it's proper, otherwise it's called improper. And that would be if the reverse of this is true. Okay, so what's mainly in this section, most of your work is going to be, as I stated up here, you going from this type of rational expression all the way back to the partial fractions that were used to create it through addition. Okay, there's going to be some rules as you go through the problems. There's different levels of difficulty with respect to these problems, which impacts how much work you have to do for each problem. So these are the basic rules. For any linear factors that occur in the denominator, and you'll see as we go along. Remember, linear means first degree. So you're going to need to factor the denominator. And when you factor the denominator, if those factors are linear, that means that you are going to break them up into partial fractions and you're going to assign a constant as the numerator for each of these linear factors. And I will use this terminology and refer back to these cases as I do each and every problem. For any irreducible, in other words, you can't factor it any further, that's where we get this word from. For any irreducible second degree factor that occurs in the denominator, so your first job is going to be to factor the denominator unless they've already given it to you in factored form. Those kind of denominators, when you begin to break it up into partial fractions, they are assigned a linear expression as the numerator. And again, I'll point that out when I get to a problem where I'm doing it. When there are repeating factors in the denominator, you must build up to the highest power of the repeating factor, one power at a time. Now, any of these things are not going to be very easy for you to understand unless I show you examples. So let's get to the examples where I can keep referring back to these cases and you can see what I'm doing. Okay, I'm going to be demonstrating this, so I'll be talking to you about that as we go along. Okay, notice that you're starting off with a single fraction here. And we're going to look at the factors that are in the denominator. We're in example 1 right here. And the factors that you are seeing in the denominator, they're both linear. You have one factor that looks like this, and that's definitely first degree, that x that's pulled out in front. So that's one of your factors. And then the other factor is that x minus 5, and that is also a linear factor. So the factors in the denominator are both linear. And anytime you have linear factors in your denominator, when you go to break these up into the partial fractions that we're going to actually try and be working towards finding the numerators of, you have to know what kind of numerators to assign to linear factors. Okay, so here is one of your linear factors. We're going to let that play the role of its own denominator. Plus, we're going to have another partial fraction where the other factor Again, both of these denominators, which came from the factors, right here, these were the factors, they're both linear, and anytime you have linear factors, you will assign a constant. We use capital letters to mean that this is a constant. We're going to be looking for this value, and because there's no x to it, we say that this is a constant, and then just call this a different constant, something different than that one. Okay, so once you break it up and decide what kind of numerators to assign based on the kind of denominators you have, and again, the denominators are just the factors here. If they are first degree, word for that, or the term for that is linear. When the denominators are first degree, you will assign constants as their numerators. And that's what it says on the previous page. Next step is to multiply this entire equation that we've created. This is the main fraction, and these are the partial fractions that we are attempting to decompose it into. The LCD will always be the product that you got these individual factors from. You don't have to give that too much thought because that's exactly where these individual denominators came from. They were just factors in what we are going to use as our LCD. Now, so that we're not going crazy with how much we're having to write out here, to pay close attention to what I'm going to do here. If something is out in front of the brackets, that means we're getting ready to multiply all of this by this fraction, and this fraction. So you have to imagine this expression right in front of this term, right in front of this term, right in front of this term, although we're not going to squash it in there. We can leave it out here and that should be fine. Okay, when we multiply it by this, I'm going to multiply it by this term right here, this entire LCD, because that's exactly what it is, cancels with everything in the denominator, leaving you just with a 15. When we multiply this entire LCD by the next fraction, let's see, this x would cancel with this x, leaving you with x minus 5 times a. So copy that equal sign, and then here's my a times x minus 5. I'll point that out to you again one more time. When you multiply this LCD times this fraction, that x cancels with that, leaving you with x minus 5 times a. I'm going to write the constant out front. Then when I use it on this last term, when I multiply this entire LCD by this x minus 5 cancels with the x minus 5, leaving you with x times b. And again, I'm going to write that constant first and then the x. Okay, the next step after you multiply by the LCD is that you are going to, as an attempt to solve for A or B, this will be the first thing that you use. You're going to think about the values. What are the values that would make this denominator 0 or this denominator 0? And after you've exhausted all those, if you haven't found all the answers, then we're going to go to another technique if we haven't found all the numerators by then. In this problem, just allowing x to be 0, because that's what would zero this denominator out, and letting x be 5, because that's what would zero this denominator out, it's going to allow you to find a and b. But sometimes we've done that as much as we possibly can, but we still haven't found all of the numbers in the numerator, and in that case we shift over to comparing all terms that are, let's say, second degree, and then comparing all terms that are first degree, or comparing all the constants. That's a technique that will get you further answers if you haven't found everything after finding the values that make, using the values that make the denominators undefined. So one value that would zero this out, making this undefined, is x equal to 0. So we're going to let x be equal to 0, and we're going to use the resulting equation. Now when I say let x be a particular value, I mean plug it right into here. So it would be 15, And if you let x be 0, in this term right here, it would be 0 take away 5, which would just be negative 5. If you put a 0 in there, 0 take away 5 is negative 5 times a. And if you put 0 in there, it just completely gets rid of that. So by letting x be equal to 0 in this equation that was created after we multiplied by the LCD, we come up with this little mini equation that allows us to solve for a. So divide by negative 5, divide by negative 5 on both sides, and you get a is equal to negative 3. So we have the numerator of this expression. Almost done. Now we need to find the numerator for this expression. And once we have found a and b, then we have the two partial fractions that this fraction decomposes into. So we've gone from the bigger singular fraction into the two partial fractions. So now let's find b. And we're going to use the other value that would create a 0 here. In other words, that would make this undefined. And that value would be 5. So now we're going to let x be equal to 5. Again, right in this equation, this one right here, where we had no fractions at that point. So just look right above. You see 15 is equal to a times x minus 5 plus bx, and that's what we're plugging these values into. Okay, so the left side has a 15, no place to plug anything in there. We got an equal sign, and if I'm using a 5 right in here, that would create a 0, 0 times a, that term would be gone. If I put a 5 in here, I'd have 5 times b. So now I have another mini equation. Divide both sides by 5, and you get b is equal to positive 3. So we now have the numerators, and we can now write our final answer. I'm going to use 3 dots, which stand for the word therefore in mathematics. Therefore, this single rational expression, 15 times over x times x minus 5, is equal to these partial fractions. We now know the numerators. A is the numerator of this term containing x in the denominator. So that value was negative 3 over x. And then the b value is assigned to the denominator of x minus 5. And we got a 3 for x minus 5. And that's the completion of the problem. This is exactly what you would be feeding into MyMathLab. You're going to show the two partial fractions that you've created and the numerators that you have found that go with them. Okay, moving on to example 2. And I believe they're only going to make you feed in this part right here, the two partial fractions. Okay, in example 2, write the partial fraction. All of them are going to say that. Notice now, though, that you have a power of 2. That means that this factor is a repetitive factor. It repeats. It's x minus 2 times x minus 2. Anytime there's a power of 2 or higher, you have a repetitive factor. Now the factor, so this is a repeating. Now look at that base. What's inside the parenthesis, forget about the 2 right now. What's inside the parenthesis is a linear expression. In other words, the expression inside here is first degree. It just happens to be a linear factor that's repeating. So this is a repeating linear factor. And as my directions on the previous page stated, whenever you have a factor that has a power on it like this, you have to build up to the power when you create your smaller partial fractions, and I'll show you how that looks. Then we have this other factor, which is just a linear factor. It does not repeat. It only occurs once. And so when you have this repeating factor, look how you create the partial fractions. You can't jump right to power 2. You have to start with power 1 and build yourself up to this power that's higher than 1. So we're going to go, one denominator is going to look like this. Okay, so that's x minus 2 to a power 1. You don't have to put the parentheses around it when it's a power of 1. I just did it. Then we're going to have another fraction where we're building up from power 1 to power 2. Creep up from power 1 all the way up to whatever this power is. It's only power 2, so we get there pretty quickly. Okay, now I have to have a parentheses on it. Okay, now both of these factors, they are linear. In other words, this expression is linear, therefore the kind of numerator that is assigned to a denominator such as this is always a constant. This is also linear. It just happens to be a linear factor that repeated. So when that base is linear, in other words, what's inside the parenthesis, again, it gets a constant assigned as its numerator. Then we also have this factor. It doesn't repeat, so we don't need to build up to it, but we did need to use the concept of building up to the power for this particular factor. Okay, so we have another fraction where the denominator is x plus 5. It is also linear, therefore it gets a constant. You have to use different variables to represent the fact that these are constants. Now this time we're looking for A, B, and C. So your go-to method for finding as many as you can is to think about the values that would zero out these denominators. One of those values is the number 2, positive 2, and the other value the positive 2 would zero this out as well as this out. So we're going to use 2, and we're also going to use negative 5 when we get to that part of the problem. Before we get to that part of the problem, we have to see what results when we multiply this rational equation by the LCD. And the LCD here is whatever you see in this very first, whatever the denominator is of this singular fraction. That's your LCD. So it's x minus 2 squared times x plus 5. Okay, any LCD out in front of these brackets means you're about to multiply it by each and every term in this equation. So always when you multiply it by the singular fraction, since this LCD that you're looking at right here matches that denominator, all of that cancels with all of that, leaving you with just the numerator x squared. Bring that equal sign down. Then when you multiply this whole LCD times this next fraction, one of these x minus 2's cancels with that x minus 2, but then you'd still have one left over here. So this really says x minus 2 times x minus 2, so one of those cancels with this. You'd have an x minus 2 left over, you'd have an x plus 5 left over times a. Okay, we'd have an x minus 2 left over. That wouldn't cancel with anything, and an x plus 5 that wouldn't cancel with anything. Okay, moving on to multiply it by this third term. If you were to multiply this entire LCD with all of this, both of these x minus 2's would cancel with both of these x minus 2's, leaving you with an x plus 5 that wouldn't cancel with anything times b. So plus b, and that x plus 5 will not have canceled with anything, so it remains. Okay, when you multiply that LCD out front by that very last term, the x plus 5 cancels with this x plus 5, and you're left with c times x minus 2 squared, which doesn't cancel with anything. So just the x plus 5 cancels for this very last product. And you have c times x minus 2 squared plus c times x minus 2 squared. So we're getting into a little tougher algebra here. Not as easy as when all the factors are linear. Okay, we said that our immediate go-to for finding as many values as we possibly can before we shift over to any other types of procedures is to think about what would cause zeros in these denominators. So 2 is one of them. So we're going to let x be equal to 2. And remember, when you're letting x be equal to whatever it is you're letting it be equal to, you're plugging it into this equation that now has no fractions. Okay, so if x was 2, anywhere you see an x, you're going to put a 2. So putting a 2 in there, you'd have 2 squared. That's on this side right here. Then if you were to put a 2 right there, that would cause a 0. And 0 times all of this would get rid of this whole term. Likewise down here. If you put a 2 in this last term, 2 minus 2 would be 0. 0 times c would get rid of the third term. It would get rid of this entire term. Because if any of these pieces is 0, that whole thing is 0. So the only thing that really remains for you to plug a 2 into, because it's not going to zero out, is going to be this middle expression. So 2 plus 5 is 7, 7b. And here we go, finding b. So if you were going to solve this, you would divide by 7, divide by 7, and you now know the b value. It is 4, 7. So we have one of our 3 values. Okay, the other thing that would cause a 0 in the denominator would be -5. So we're going to let x be equal to -5. Okay, go right through this equation again, letting anywhere that you see an x, plugging in a -5. So if you plugged in a -5 right there, you'd have 25. -5 times -5 is 25. And if you plugged in a -5 into this first expression, you'd be putting a -5 right there, causing a 0 to happen. So 0 times whatever's here would cause this whole thing to go away. If you put a -5 right here, this whole term would go away. So this and this would zero out based on you plugging in a -5 for x. However, when you get down here, plug in -5, take away yet another 2, which would give you -7 times c. Okay. And let me just check this real quick. X plus 5, just checking all my numbers. Oh, okay, I see something right here. Okay, yeah, I didn't see this little 2. There's a square right on here, so let me do that again. When you plug in -5, right there you get the 25. Putting -5 in there, that whole thing would zero out. Putting in -5 right there, that would zero out. This one, all I did was plug in the -5 and I called it a 7, but it's actually -5 take away 2 is -7, and that square, which I did not see just now, that makes it -7 times -7, so that should have been 49c. So let me fix that. Before I get deeper into the problem, that should have been a 49c. Okay, so here you have another little mini equation, just like this one. And if you just divide by 49 here, as well as here, you have c is equal to 25 over 49. So the only thing that remains is for us to find the a value. So another technique that you can use when you've exhausted all the numbers that could potentially make these denominators 0 is to move to a technique where you're comparing terms that have the same degree. We are specifically going to compare actually the coefficients of terms that have the same degree. So for instance, why don't we compare second degree coefficients. You can start there. Second degree coefficients. Okay, first let's identify all the second degree terms. Again, let's look right here. Let's look at this equation that is fraction free, not back up here. So if we compare second degree terms on the left and the right side, on the left side we have this term, x to the second degree, and then let's go pick out all the second degree terms on the right side. Like for instance, if you were to begin foiling this out, the very first product that you would do right here, first times first, would be your second degree term. You'd have x squared times a. You don't care about any of the other terms. We're only looking for second degree terms in this particular comparison that we're doing, because you can compare first degree terms and then you'd only be looking for first degree terms. You can compare constants and then you'd only be picking out the constants. We're only comparing second degree terms here, and that's why I'm only worried about the second degree terms. So here's one right here, x squared times a. And then over here, there's no second degree terms. Definitely here, there's a second degree term, because remember I taught you a shortcut for getting this a binomial all squared out, and that's square double square, if you remember this. I mean, really, we don't really need to worry about the double and the second square, because squaring this first term right here is what gets you the squared term. When you double, that's a linear term, and when you square again the second time, that's just get you a constant. I'm only worried about the x to the second degree, and anything I get from square double square is going to be multiplied by that c. So we have a positive c x squared. Now when I say compare the coefficients, I think the first thing you should do is find the kind of terms you're looking for. I've done that. Now we're going to go to comparing just the coefficients to get our third and final little mini equation like we created here, which is going to possibly allow us to get a. Let's see if this works. Okay, we're going to clip off all of the coefficients. Okay, coefficient of this x squared term on the left is a 1. The coefficients of the x squared terms on the right are a plus c. Only grabbing those coefficients. Okay, so I finally now have an equation with a in it, which can potentially allow me to solve for a. And based on the fact that I already know what c is, I could just substitute it right here so that I only have one unknown, and that will allow me to solve for a. So I'm going to put my c value right in here. And I have a 1 over here. And if you were going to solve this, you would subtract 25 over 49 and subtract 25 over 49 on the left side as well. These would cancel, leaving you with a, and you could always get your calculator to help you out with this part right here. That would just be 1 minus 25 divided by 49, and instead of hitting enter, hit math, enter, enter, since there's fractions involved, because that will take care of all of the simplification that you need to do. So that was 24 over 49 that we just got. Okay, we now have all three numerators, so in the end, we're going to rewrite this, giving each of these partial fractions with their numerators intact now that we found them. So, in the end, it is the fraction x squared over, let's see if I have enough room to write this, over x minus 2 squared times x plus 5. And that breaks up into the partial fractions a over x minus 2. And we found out that our a value is 24 over 49. That is the numerator. Lots of times you'll get fractions when you're doing partial fraction decomposition. Over the denominator, x minus 2. Then for the next fraction, where the denominator was x minus 2 squared. Go ahead and write that denominator. The numerator that belongs to that denominator is b, and we found out that b was 4/7. And then in this last fraction, where the denominator was x plus 5, the denominator assigned to that was c, and we found out that c was 25/49. So you have taken this single fraction and decomposed it into these 3 partial fractions, doing all our work trying to find those numerators. Okay, moving on. So that was a case where one of the linear factors repeats, and we built up to that power of 2, 1 degree at a time. We tried it first to the first degree, and then the second time it was mentioned, we had already built up to the second degree, because you're only having to pass through power 1 and power 2 to get up to power, ultimately get up to power 2 on that particular factor. And then there was this other factor. So that was an example of building up to a repetitive power on a factor. Okay, this is an example of having a factor in a denominator that's irreducible. In other words, you cannot factor it down any further. So remember how to factor this. Let me just give you a little review on how to factor the difference of cubes. Okay, it factors like this. You have 2 terms in here, and then this one has 3 terms. So in the first parenthesis, in the binomial, it's just the cube root of each of these. Cube root of x cubed is x. This is the factoring procedure for difference of cubes. Cube root of that is 3. So I'll just kind of write this here to remind you how you factor difference of cube. You begin by taking the cube root of each one and matching that sign. Then to get the 3 terms here, which is going to be your irreducible quadratic expression, the formula goes like this. Once you take the cube roots, you're going to look at each of these cube roots and you're going to square, multiply, square. That's how you get the other factor that has 3 terms in it and is second degree. So when you square, you're squaring that first cube root that you got. When you multiply, you're multiplying these 2. We'll talk about the signs in a minute. And the second time you square, you're squaring that back number. Okay? Last term, always positive. This term, opposite of that when you're using the algorithm for factoring the difference of cubes. So if that's a minus, this is a plus. Okay, so those are your factors. Do not bother trying to factor this any further. It is irreducible. It cannot be factored any further. So let's start building our partial fractions. We need a fraction where this is the denominator. We need a fraction where this is the denominator. Okay, any time the denominator is linear, as this one is, it gets assigned a constant, meaning there's no x term here, a constant as the numerator. And now here we go into a case that we haven't touched upon yet, when the denominator is second degree, as we have here with this factor. We have a factor that is second degree. In that case, your numerator is not a constant, it's a linear expression. A linear expression has an x to the first degree and a constant. So we're going to have x to the first degree with a coefficient, call it something different than that, and then also a constant. That's how your linear expressions will be designed. X to the first degree term with a constant different than you've used thus far, and then a constant, another constant. Okay, so that's what I meant by when you have a second degree irreducible quadratic expression as your denominator, then this expression has to be 1 degree less than this. Okay, so we're going to set off trying to find out what A, B, and C is, because as soon as you find the numerator values, you're done. Okay, remember we always start off by getting rid of these fractions, and that just takes multiplying by the LCD, but you want to put the LCD out here in factored form, or else you're not going to see what cancels when you get on this side. So don't leave it like that. Take these factors and throw them out here. Always you'll find your LCD under the main fraction. So x minus 3 times x squared plus 3x, trying to squeeze everything in here, plus 9. Okay, moving on. And as we have done in each of these problems, as soon as we find the LCD, we have to multiply that LCD by each and every term in this rational equation. So always the LCD for the first fraction, that whole thing is going to wipe out this whole denominator and leave you just with the numerator. Okay, that's after doing a product of the LCD with this first fraction. Always this entire thing cancels with the entire bottom, leaving you with just what's in the numerator. Then you're going to multiply that LCD by the next fraction. Okay, pay attention to what cancels. This x minus 3 right out here would cancel with this x minus 3, leaving you with this a times this factor that doesn't cancel with anything. So all of that times a. Then when you multiply it by the third fraction, this entire quadratic expression, x squared plus 3x plus 9, all of that cancels with all of this, and you'd just be left with x minus 3. It's got nothing to cancel with in the case of this third fraction. Only this cancels with this, leaving you with x minus 3 times that entire numerator. So bring that plus sign down. X minus 3 is left over, doesn't cancel with anything, times this entire numerator. It does not cancel with anything. So now we have an equation that has no fractions, and we can go into beginning to find A, B, and C. Remember, your go-to method, the easiest way to find any of the values, is to consider whether or not there are any numbers that would zero out these fractions. Okay, because you cannot break this down any further, there's not going to be anything that can help you zero this out, but there is something that you can use here, and that number is 3. Okay, so let's first evaluate in the situation where x is equal to 3. The number that would zero this out, thereby making this fraction undefined. So we're going to take a look at what we can get by letting x equal to 3, and always in this equation that we just created in the step above where we no longer have any fractions. Okay, so if we let x equal 3, there's nowhere to plug in here, so that left side is going to stay as it is regardless of what we're plugging in. But then we can plug in the 3 right here, that would be 9. If we plug in a 3 again here, that would be 9 plus 9 plus 9, which is 27. You can use your calculator as much as you want as you're doing this. Again, 3 squared is 9. 3 times 3 is 9, plus this additional 9. So 9 plus 9 plus 9 is 27 times A, which occurs by plugging in 3 for x. So 27A. Let's move on here. By the time you get to this second product, if you are plugging in 3, it would make this factor 0, and 0 times whatever is here would just get rid of that entire expression. So we're left with this little equation here, and if we just divide both sides by 27, then we get our A value. And reduce that. 3 goes into the top 1 time, 3 goes into the bottom 9 times, and it is negative. So we at least have one value. But that's all we have as far as values that will zero out the denominators. Remember, when you're looking for those values that zero out the denominator, you're only looking on the side where the partial fractions are. There is not, if I could have broken this down to linear factors, then if I could have continued to factor this and I got linear factors, then there could have possibly been some more numbers that would zero out this denominator, but this didn't factor any further. So I did the best I could with finding numbers that zero out the denominator, and now I'm going to move to the procedure where I compare the coefficients of like degrees. Okay, I'm going to start with second degree. So I'm going to compare second degree coefficients ultimately. I'll start with the actual terms. And then I'll use just their coefficients. Okay, let's see. So there are no second degree terms on the left side. There are 0 second degree terms. On this side, we have 1 second degree term here times this coefficient. So that's one of them. And then right here, if we were to multiply this out, just doing the first step where you actually get the second degree term, because that's all we're interested in right now, you'd have x times bx, which would be bx squared. So that's another second degree term. Okay, once you've identified all the second degree terms, you are then to only compare the coefficients. Then strip those coefficients right off of the variables and work just with those. So it is 0 without that second degree term is equal to a plus b. Use just the coefficients. At that point you have this equation, but we already know what a is, so we can take this value and plug it right in here. So we have -1/9 for a plus b, which is equal to 0. And if we just simply add 1/9 to both sides, that will move this 1/9 over here. Add 1/9, add 1/9, and you have what b is. B is equal to 1/9. Now we have two values. Okay, let's continue. We still don't have all three values, so why don't we compare first degree terms? Okay, let's see. If we compare first degree, ultimately we're going to be comparing the coefficients, but right now we need to just point out to ourselves what are the first degree terms on the left as well as the right side of the equation. Okay, so on the left side of this equation, all you have is a -3. There are no first degree terms. There are 0 of the first degree term, x to the first degree. Over here, that's a first degree term, so it would be 3x times a. So 3 times a times x, where the 3a is the coefficient. Okay, then moving down here, let's see, you'd have a couple of linear terms here. That would give you the squared term. Then it would be x times c. Well, let's just write out, let's just FOIL this out. You would have bx squared. We already used that when we compared second degree terms. Then, and that's when you go x times bx. Then when you go x times c, that would be cx. That's a first degree term. Then you would go this term right here, and that's also a first degree term. It'd be -3 times b times x. -3 times b times x, where that -3b is the coefficient of this term. So let's see. Okay, so we already talked about how a times 3x is one of the first degree terms on the right hand side. Then here's another one, cx, and this -3bx is yet another linear term. So we're comparing all first degree terms on the left to all first degree terms on the right. Okay, now we're going to go into the part where we strip away the variables and only compare the coefficients. Okay, coefficient on this side, 0. Coefficient of the x terms here are 3a, c, and negative 3b. 3a, positive c, and negative 3b are the coefficients of the three linear terms on the right-hand side of this equation. Okay, now two of these values we already know. We know that a value is negative 1/9. We don't know the c value in the middle, and we know the b value. The b value is positive 1/9. Okay, so we're going to do a little bit of arithmetic here. This is 3/9 or 1/3. Got that c in the middle. This is 3/9 or 1/3. It just happens to be negative. And if we clean this up a little bit, it'd be negative 1/3, and negative 1/3 is negative 2/3 plus c. Drop that 0 down. And if you want to solve for c, you need to move this term. In other words, add 2/3, add 2/3 to each side. That'll make this jump over to the left-hand side, and you will have c is equal to positive 2/3. Okay, we now have all three values. We have the a for this numerator, and we have the b and the c value that we needed for this numerator. So all of this, I don't have too much room here, but I guess I can write it up here. I'm going to try and fit it right up here. Okay, so therefore the singular fraction, negative 3 over x cubed minus 27, the one we started with, is equal to these partial fractions, having a denominator of x minus 3 with a as its numerator, and the a value turned out to be negative 1/9. Then moving on to the next numerator, which was associated with this denominator, x squared plus 3x plus 9. And that denominator was, and that numerator was bx plus c. Our b value was 1/9, so 1/9 times x. And you can put the x right out here, or you can just multiply it right into the top. Don't drop it below that bar. So it's bx plus c, the c value being 2/3. When you type this into MyMathLab, you can just type it in as x over 9 plus 2/3 for this particular numerator. Okay, and that completes that problem. So that was one of the partial fractions. This is the other partial fraction. Okay, moving on to our last problems. These have quite a bit of work, so I've covered all the cases that were mentioned on the previous page with these examples. There's only 6 problems, and I believe in MyMathLab the first couple are just about terminology. And then there's 4 examples. So I've grabbed one of each of what you're going to be seeing, the type that you're going to be seeing, which goes through all those cases on the previous page. Okay, here we come now. We have another factor repeating, only this time it is a quadratic term. So we have a quadratic, and you can't reduce that. You cannot factor that any further. So that's irreducible as far as factoring capabilities. So it's, let's see, let me write it like this. It's a repetitive, it repeats twice. This repeats twice. It's a repetitive quadratic second degree factor. Okay, and remember, whenever anything repeats with its power, you have to build up to it. So first we're going to see this base, this quadratic base, to the first degree, then we'll build up to second degree. So here's going to be one of our fractions. You can't factor this any further. What's inside just does not factor. Difference of squares factors, but not sum of 2 squares. And we got this repetitive situation going on. So we're going to have that quadratic base to the first degree. And if it's to the first degree, you don't have to wrap it in parentheses. And then the numerator, we'll talk about that in a minute. And then the next denominator is going to be that same quadratic base, but building up now from first degree, this is first degree, to second degree. Okay, here we say it's appearing to the first degree because if I was to put a parenthesis with no power up here, that power is said to be 1. So here you have this quadratic expression to the first degree. Here you have the quadratic expression to the second degree. So I have built up to that repetitive power of 2. And now I have to remember, hey, what kind of numerators do I assign to denominators of this nature whenever it is second degree, just like in this problem. When that denominator is second degree, you will assign it a linear expression, meaning it'll have an x to the first degree term and a constant. So I am going to let this one have the linear expression ax plus b. But this also has to have a linear expression in its numerator because the base is quadratic. Anything quadratic like this gets a linear expression as its numerator. Okay, so this time instead of ax plus b, I'll call it cx plus d. The coefficients here have to be different than those. Okay, here we go into the step where we get rid of all these fractions by multiplying by the LCD, which can always be found in this single fraction at the bottom. So this is LCD, and the LCD, what it does is it always gets rid of all the fractions. Okay, so consider that you are multiplying it by this, and by this. Each time that LCD is going to cancel with something different. Always in the first fraction, this entire LCD cancels with the denominator in the first fraction. This matches this perfectly, so they cancel, leaving just the numerator. So x squared plus 2x minus 4. When you multiply it by the second fraction, one of the x squared plus 4, because look, it repeats. It's x squared plus 4 and then x squared plus 4 again. So one of them cancels with this, having one of these left over times ax plus b. We'll keep it in parentheses since there's 2 terms in that expression. So one of these cancels with this. You'd have one of these left over times ax plus b. When you multiply this LCD times the third fraction, this entire x squared plus 4 to the second degree cancels with this, x squared plus 4 to the second degree, and leaves you with just the numerator. Okay, now we have an equation that does not have any fractions. You can't go into this problem and use what we have used in several of these problems where we look at, hey, what values might make the denominator 0, because these can't be factored down to linear factors. There's no value that would possibly make this 0. That's impossible here, here, or here. So you have to completely rely on the technique of comparing the coefficients of same degree terms. Okay, let's start off with, we actually have third degree in this problem. Why don't we start there? Okay, we're going to compare third degree. Ultimately going for the coefficients. Okay, on the left side, there are 0 of the third degree term. There are none. On the right side, if you were to do this product right here, in this foiling, you don't have to go through the whole thing. Just consider the kind of terms we're looking for right now. X squared times AX would be AX cubed. Down here, there are no third degree terms. So you've actually found all the third degree terms that exist. Now snap off those coefficients. You're only using the coefficients. So take off the variables, and you already know that A is equal to 0. Okay, let's go down a degree. Now let's compare second degree. Now you're going to compare second degree coefficients. Okay, we'll run through that same equation, only this time trying to look for anything that's second degree. On the left-hand side, we have second degree, 1x squared. Then over here, let's see, we'd have a third degree term. Here's a second degree term, x squared times b. If we were to continue foiling, that first product gave us an ax cubed, but then when you multiply x squared times b, you have bx squared. This would just give you x to the first degree, 4ax, that's just first degree, and 4 times b, that's just a constant because it has no x at all. We have no more second degree terms here. So we're done with the second degree terms. So now remember, you're always trying to zero in on just the coefficients when all is said and done. After you've picked out all the whatever kind of term you're on, after you've picked out all the third degree terms, then just take off those coefficients. Same thing here. Let's go with the coefficients. Coefficient of this guy is 1. Coefficient of this is b. So now we know b. Okay, we still have C and D to find. So let's keep going. Let's compare first degree. So this problem really gives you a big, many opportunities to use this technique where you're comparing the coefficient of terms that have the same degree. So compare first degree coefficients. Okay, let's see. We have a first degree term on the left, 2x. Anything that has x to the first degree. Over here, let's see, we had x cubed, we have bx squared. Right here, if we continued the foiling, we would have 4a times x, so that's 1. 4a times x. And then that last thing is just the constant. Then if we come down here, there is a linear term right there. Okay, now remember, as soon as you pick out all the terms that you are interested in, then it's time to just take off the coefficients. So the coefficient of this first degree term, 2. Coefficient of this first degree term, 4a. Coefficient of this first degree term, c. Okay, but we already know that a is 0, so we can go right in there and plug in. And if you're going to put a 0 in right in here, that would be gone, leaving you just with C. So we now know C. All right, we have compared third degree, second degree, first degree. And now we're going to go with, the only thing left to compare is the constants. Those are considered the 0 degree terms. So compare the constants. Okay, and if we're looking for those constants, let's see. On the left side, we have a -4. That's a constant. And now let's go pick out all the constants on the right side. So reviewing this again, third degree, second degree. This would have been first degree. We did that already. And now 4 times b, if you were on the last part of this foiling, 4 times b would be a constant because it has no x's in it. Okay, coming down here, the only constant is this d. Okay, then don't forget, after you've selected all of the terms that satisfy the kind of terms you're looking for. We were only looking for terms that are constants. Then you just want to look at the coefficients, and that's important when they have x's on them. You have to actually take off the coefficients, but you can't really strip, there's no x's that you can peel these away from, so we're going to go ahead and see what we can figure out here for D. We already know the B value. We know that the B value is 1, so if we go and put that 1 right in here, and we leave this D right here, we would have negative 4 is equal to 4 plus D. And if we wanted to solve for D, we could subtract 4, that would get rid of this and leave us with D is equal to negative 8. So now we have all of our values and we can give our final answer. So in the end, we're going to say that the main fraction, x squared plus 2x minus 4 over x squared plus 4 to a power of 2 is equal to this partial fraction breakdown, ax plus b over x squared plus 4 okay, a is 0, so this would be 0 plus whatever b is, and b is 1. So that would be the first fraction. And then the next fraction would be cx plus d over x squared plus 4 raised to a power of 2. Okay, c was 2, so it would be 2x plus d. D turned out to be negative 8. And that is assigned to this denominator, x squared plus 4 raised to a power of 2. So, to see why we're only doing 4 examples, because these are pretty long. But we have covered all bases mentioned on the previous page. We looked at what kind of numerators to assign when the denominator is linear, such as in this case, you assign a constant. We also looked at what kind of numerator to assign when it's second degree. And then we also got into some repetitive cases. One on the previous page, and then here was another one where this base repeated. On the previous page, we had a repetitive case, only this base was linear, whereas this base was second degree. So that made both of these numerators had to be linear expressions, and that took quite a bit of work. I would suggest that if you do have to fall back to the technique where you're comparing the coefficients of like degreed terms, that you start with the highest degree in the problem and work your way down. And you probably noticed that I did that every time I fell back to this method where I was comparing coefficients. I started with the highest degree, and then I went down to the lowest degree. Okay, so that completes section 11.5.